Now, this chapter is a review of power series from Calculus 2. I've split this into 3 parts. You're welcome to skip any or all of this if you're already knowledgeable in power series from Calculus 2. And here's what we mean by power series. We mean we have polynomials that have increasing powers of x. So as you can see here in the first one, we've got an x to the 1, an x to the 2, x to the 3, x to the 4 going forever. Same thing with the second one, x to the 1, x to the 2, x to the 3, x to the 4, and so on. All of these are polynomials with increasing exponents that go forever. So that's a power series. We use the terminology centered at 0 simply to mean that we have no translation going on. This is just an x, not an x minus 1 or an x minus 2 or something like that. And so all of this is centered at 0. Here's what the ones look like that are centered elsewhere. For example, if this was centered at 1, then this would say x minus 1. All of the x minus c's would be x minus 1. If, however, it was centered at, say, 2, then these would say x minus 2. Everywhere there's a c, it would be a 2. That would be centered at 2. Now I'm going to show you the idea behind the power series by coming up with the power series to represent the transcendental function e to the x. And we're going to use the p to represent the power series, the polynomial that we're coming up with. I've got this color-coded for you. And then the f of x, of course, is the function we're trying to convert to a polynomial or to a power series. Now here's the graph of e to the x, and we're saying that we want to center our polynomial at x equals 0. The first requirement we're going to have is that the value of our polynomial and the value of the function we're trying to describe with our polynomial be the same when x is a 0. So that means that f of 0, which would be e to the 0, which is a 1, we want our polynomial to also have a value of 1 when x is 0. So we're just going to say p of x equals 1. Now here's the graph of e to the x, and here's the graph of the polynomial p of x. Notice the only value they have in common is the point 0, 1. So this is not a very good representation of the function. So we're going to continue on. We would like for our polynomial to have the same slope then as the function. Well, remember the slope is the derivative. So if we do the derivative of the function at x equals 0, we need our polynomial to also have a slope of 1. So this is a first degree polynomial with a slope of 1. Now notice when we put our polynomial on the graph along with the function that they now have more points in common, a little larger range where they're the same than previously. Now we'll also want the curvature of our polynomial to be the same as the curvature of the function. The curvature, if you remember from Calculus 1, is the second derivative. And so we want the second derivative of the function at x equals 0 to be the same as the second derivative of our polynomial. So let's figure out what a sub 2 would have to be. Here's the first derivative, here's the second derivative. So these would have to be equal. In order for them to be equal, a2 would have to be a 1/2. So here is the second degree polynomial, which we're claiming is a good match for the function e to the x. So on the graph of e to the x, we'll overlay the polynomial 1 plus x plus 1/2 x squared. Notice again how now there is an even larger area where the values match. Now, we'll simply say then, having done the previous two, we would like for the third derivatives to match. So here's the process, much like what we just did. We take our function, do its third derivative at 0. We take our polynomial, use a sub 3 for the coefficient of x cubed, do the third derivative, and make them match. Well, you can see a3 would have to be a 1/6. So here's the polynomial. And here's the graph of that polynomial. Again, notice how there's an even larger matching of the two. Likewise, here's the fourth derivative of the function and the polynomial. And so the coefficient of x to the 4 would have to be a 1/24. Here's the graph of both. Now typically what we do when working with series like we're doing now is, having just done this several times, we might recognize some shortcuts. For example, the pattern. You notice the next term of the polynomial is going to be an x to the 5. It would be nice if you recognized this relationship for these numbers and these numbers. So, having shown you what I just showed you, do you know what would go here without actually doing those calculations? Well, the number for x to the 5, since this one was 4 factorial, and this one was 3 factorial, and this one was 2 factorial, this one probably is going to be a 5 factorial. Likewise, this one should be a 6 factorial. So we can real quickly create the next few terms, and we could even continue going with this pattern once we know the pattern. Now here's the graph of that 6th degree polynomial that we just came up with. And again, notice the region where they match is significantly larger this time than it was before. So let me show you what we mean by a Maclaurin polynomial. As you can see here, we're talking about a polynomial where we're using a sub 0 here to mean the constant term. A1 is the coefficient of x to the 1, a sub 2, coefficient of x to the 2, a sub 3, coefficient of x to the 3, and so on. Now here's the derivative, second derivative, and so on. Now we've already done this, so I'm not going to spend a lot of time explaining it other than to say go back over what I just showed you and come back and look at this slower if you need to. Like I did with the e to the x function, we would like for the value of this polynomial at x equals 0 to be equal to the function that this polynomial came from, which we're calling f. And so we would like p of 0 to be equal to f of 0. Well, p of 0, notice, comes out to be just the a sub 0. So we would like that to be just a sub 0. F of 0 is a sub 0. And like we did with the e to the x, we would like for the derivatives to match. And for x equals 0, we get a sub 1. So we need f prime of 0 to be equal to a sub 1. Well, that means that a sub 1 is f prime of 0. Now here it starts changing a little bit. Notice when we use a 0 for x, every term cancels except for the first one. Now if f double prime is equal to 2 times a sub 2, then a sub 2 has to be f double prime divided by 2. Likewise, for the third derivative at 0, we need f triple prime to be equal to 6 a sub 3. So a sub 3 would be f triple prime divided by 6, which we'll write as 3 factorial. You'll see why shortly. And so on. Now, I'm not going to continue with all of these, but do you see a pattern evolving here? Let me just point out that this 2 matches 2, 3 matches 3, 4 matches 4, and so on. Let me point out that we didn't write a 1 factorial here because it is just a 1. Let me also point out that 0 factorial is also a 1. So here is the formula that we call the Maclaurin polynomial. Now, if we say that we're centering somewhere besides 0, that just means that we have a translated polynomial. So everything that we just said about the Maclaurin polynomial would still be true, only we would have the value of c as the number where we were centering our polynomial. And these are referred to as Taylor polynomials. Let me point out that a lot of people, textbooks included, use the term Taylor polynomial for all approximating polynomials. And a Taylor polynomial, when c equals 0, is a Maclaurin polynomial. Now, using that formula, we can find the 6th degree Maclaurin polynomial for cosine of x by doing each derivative and substituting a 0, which is where we're centering it, all the way up through the 6th derivative. And then put those into the formula that we just derived. And that can be simplified some by removing the terms that are zeros. So here is the 6th degree polynomial, which we claim approximates the cosine function. Notice this is a pretty good approximation for certain values of x, but not for others. And I'll show you this last one real quick that is centered at 1 instead of at 0. Now again, all the stuff that you do is the same. You do the function value at 1, you do the derivative at 1, you do the second derivative at 1, the third derivative at 1, and the fourth derivative at 1. Since we're only doing a 4th degree polynomial, we can stop there. And then we put all of those into the formula. Some of those are zeros, first one that is, and so we can simplify that. And there's our fourth degree polynomial centered at 1 that represents the ln of x. Here's the graph, and again you can see matching graphs close to 1.